Hi students. In this second video for online lecture 7, we are now going to talk about two other important periodic trends, that being of ionization energy and electron affinity. So let us go ahead and look at ionization energy first. This is the minimum energy in kilojoules per mole required to remove an electron from a gaseous atom in its ground state. So what does it mean by remove? This means that we are going to bring in some amount of energy, which we will call the ionization energy, to forcibly remove an electron. We saw this in the previous chapter that we are going to give that electron enough energy to go to an electron state far, far away, going towards the limit of infinity. It is no longer going to be attached to the atom. So now once that happens, we are going to form a positively charged cation. Well, if a species has more than one electron, we can do this again. We can go and attack that cation and try to remove another electron. If we do this, we must label this the second ionization energy. Well, doing something twice is fun, but can we do it further? If we even have more electrons, we can go and do it a third, a fourth, a fifth time. We can forcibly remove all of the electrons on an atom if we so choose. We would call this the third ionization energy. The important trend, however, in ionization energy can be summed up right here, and that is saying that the first ionization energy is weaker than the second, than the third. But how is that possible? Well, as you can see here by this first ionization energy, I form a positively charged species. So then when I have my second ionization energy attempt, I am trying to remove an electron from a positively charged entity. That is going to be much harder. So just imagine that removing an electron is going to increase the effective nuclear charge. Increasing the effective nuclear charge is going to raise the ionization energy because we're going to need more energy in order to remove the next electron. So now, as you can see, after my second ionization energy, I have something that is now 2 plus. This is going to be even harder. I've increased the effective nuclear charge even more. So finally, when I get to my third ionization energy, this energy is going to have to be much, much greater in order for us to go and get our electron to be removed. So here are the ionization energies for the first 20 elements. There are very important things that I want you to notice based off of this table. First off, with hydrogen, you have only one ionization energy because there's only a one electron. You can only take as many electrons as an atom has. So then notice with helium, we can take 2 electrons. But the important part then becomes with lithium. Notice here for our lithium, we have a first ionization energy of 520 kilojoules per mole. This is because we have now populated the 2s orbital. Look at the dramatic energy change that now goes into our second and third ionization energies. This is because these 2 electrons are now considered core electrons, and they would be in our 1s orbital. So if you see a very large increase in ionization energy, you might very well be attacking what was once core electrons and a full shell or subshell. So let's go ahead and look at beryllium. Notice that for beryllium, we are going to have our 2s electrons here, and then look at this massive jump going to our third ionization energy. This is because we are now trying to attack the 1s electrons again. So, other things that we want to look at. We know that lithium is an alkali metal. Let us go and look at sodium, which is the alkali metal below. And then finally, let us go and look at potassium. Notice that as you have the first ionization energy of an element further down the periodic table in a family, our ionization energy is going to decrease. This is because our electrons are getting further away. We have a reduced effective nuclear charge, and that means it's going to be easier to take those electrons away. So as you go down the periodic table, you can expect the ionization energies to decrease. Now, let's go ahead and look as we go horizontally across a period in the periodic table. So we can go from our lithium to beryllium. Notice this was 2s. So what happens here with all of a sudden we get a drop when we are going down to boron? Well, boron has one electron in a 2p orbital all by itself. That electron all by itself is actually really easy to remove. But then notice that as we go and do the second ionization energy for boron, we get a large jump because now we're going to start taking a full 2s subshell. However, if we go from boron to carbon to nitrogen to oxygen to fluorine to neon, notice that the general trend is an increase in energy. They become more difficult. One thing I do want to highlight very quickly, however, is this between oxygen and nitrogen. Notice that oxygen has a slight dip in our energy. This means that it's actually easier to remove an electron from oxygen than it is from nitrogen. How can that be the case? Let us go and look at the 2p subshells for our oxygen and our nitrogen. So for nitrogen, we are going to have 3 unpaired electrons. This is half-filled, Hund's compliant. In the case of oxygen, however, seeing that we have 1 more electron, notice that we have one that is paired up. This dip in our energy is trying to remove this paired electron because it doesn't want to have that in there. It would prefer to be Hund's compliant. So if you ever see a small dip in energy in which you're not expecting it, it is probably trying to reduce our electron pairing due to the electrons being repelled by each other in the same orbital. Now let's look at the full periodic table. The thing that you want to notice here is look at which species have the highest energies. Our helium is a filled principal quantum number of 1 shell. Neon is 2, argon is 3, and krypton and xenon are 4 and 5 respectively. Notice that if we have a full shell, we do not want to forcibly remove an electron. So if we have an atom that is near this and we get to a full shell, that is when we are going to see our massive jumps in energy that we are going to have to deal with. One of the other important things is that you will notice that when we get to our transition metals here, as well as here, that we just see a general trend historically of a slight increase in ionization energy due to the effective nuclear charge. But as we're looking at this, the best trend that we can have for our ionization energy can be seen here. As we go up the periodic table, we would expect our first ionization energy to increase. Another way of looking at it, as it would decrease as we go down. The further the electrons are from the nucleus, the more they are shielded from the effective nuclear charge, making it easier to remove. As we go from left to right, we will increase the first ionization energy. It will become more difficult unless we are using and removing an electron that is all by itself in a previously unfilled orbital set. So versions of that you will typically see are the 3A groups and R1A groups. Those groups have typically lower first ionization energies because we want to remove a single solitary electron that is by itself. So let's go ahead and look at this example that we have here. Which atom should have a smaller first ionization energy, oxygen or sulfur? So as you can see that they are both in the 6A group. Who would you expect to have a smaller first ionization energy? Well, what does that mean? A smaller first ionization energy means that it's easier to remove. Why is this the case? Well, sulfur is going to have its valence electrons further away and is going to have a reduced effective nuclear charge. So in this case, we would expect it to be easier to remove the electrons on sulfur. So for our question A, sulfur is the correct answer. Now let's look at B. Which atom should have a higher second ionization energy, lithium or beryllium? So let us go and do a little bit of an orbital diagram for both. So for lithium, we are going to have 1s2, 2s1, and for beryllium, we are going to have 1s2, 2s2. So now let's talk about the first ionization energy. If I were to remove an electron, the first ionization energy would remove the 2s1 electron from lithium and the compliant pair that we have here. So after the first ionization energy, our lithium would be 1s2, while our beryllium would end up being 1s2, 2s1. I think we can all agree that the first ionization energy for beryllium would be higher because we are taking from a full subshell that you see here as 2s. But this is not what we're asking. We need to know about the second ionization energy. So now let us look at our new electron configuration, and you will now notice that in for my second ionization energy, I'm going to go and attack a full shell. This resembles that of our helium. So this is going to have a massive jump in energy. So it is going to become inevitably much harder. For beryllium, we're now going to go and attack a electron that is all by itself in the 2s. So for our second ionization energy, our lithium is going to have a much, much higher second ionization energy because we're taking from core electrons and we have increased the effective nuclear charge. Our beryllium will have had the higher first ionization energy, but for the second one, it is actually going to be easier than that of lithium because that 2s1 electron is all by itself. It's really important that you use the periodic table to understand these fundamental trends. The other trend that we're going to talk about is what we call electron affinity. This is the negative of the energy change that occurs when an electron is accepted by an atom in the gaseous state to form our anion. Just remember that our ionization energy always formed the positively charged cation. Our electron affinity will always form our anion. So what does that mean? We are going to forcibly give an atom an electron and turn it into our anionic negatively charged species. Now, there are some atoms that would prefer this, and then there are going to be some that fight back. This is the energy change that we are looking for. So, if we look at fluorine, fluorine has a 2p5 subshell. Adding that electron is now going to give us the ability to go to 2p6 and be our noble gas compliant. So what happens is that this reaction is highly exothermic. It releases a lot of energy. Seeing that we're going to use delta H so often, what we end up doing is changing this to a positive nomenclature, and we say that the electron affinity is a positive 328 kilojoules per mole. Personally, I am a fan of the delta H notation. This is how I learned this back when I was in undergrad, and I prefer to have the highly negative delta H's be the species that I know that really want electrons. However, some textbooks do like the positive notation, so you just want to come up with an idea of what works best for you. So now let's look at oxygen. Oxygen now is going to be 2p4. Will it want to pick up an electron? Well, yes, it is going to want to pick up an electron, but if it only picks up one, well, this is not going to be a full subshell. So you'll notice that there is going to be less energy given off. So giving off energy, in this case delta H, is a good thing. This shows that an atom really, really, really wanted an electron. So we can see that fluorine wanted that. Our oxygen, not as much. You can see that our electron affinity has gone and dropped and gone to 141. So now let us look at our common electron affinity values. This is using the EA positive notation. So just imagine that all numbers that you see on here are going to be very large and negative if you're thinking of the delta H notation. So let's take a look at this. Why does our hydrogen want to go and actually release energy? Well, it's very simple. If I take hydrogen, even though it has one electron, and I were to add one electron, I would actually get the hydride anion, which then has the same electron configuration of that of my helium. That is incredibly stable. So having 73 kilojoules of our electron affinity shows that we are going to get some benefit by giving it an electron. A couple of things that you want to notice here. Take a look at all of our noble gases. These do not want an electron. The reason why is that we would end up populating the next s orbital in a higher principal quantum number. That means that we would reduce the effective nuclear charge, and that electron would go further away, everything that the atom doesn't want to do. So the other group that you want to take a look at here is look at the 2A group. As you can see here, these atoms have very, very low electron affinities. Well, why is that the case? Because most of this group is going to be some S2. They have a full subshell. By adding an electron, going from beryllium towards that of boron, you're now populating a p orbital to p1. So now all of a sudden, you're taking an electron, adding it in, and populating an orbital that was previously unoccupied. The other group that historically gives people a little bit of trouble is typically our 5A group. Let us go and look at our nitrogen, phosphorus, arsenic in this group right here. It's very interesting that nitrogen was brought up during our ionization energy, and this is a confirmation of our Hund's rule. So remember that our nitrogen is going to have one electron in each of its p orbitals. Why would it want to add another electron? If it adds another electron, it is going to have a partially filled, non-Hund compliant subshell, and you're going to end up getting electron repulsion in one of the orbitals. So this is why it does not want to accept an electron, and as you can see here, you have an incredibly awful electron affinity. Another trend that you want to see very quickly is notices that you go down the periodic table inside of your families. Historically, you are going to get less electron affinities because the electrons are getting further away and you have a reduced effective nuclear charge. Here is our electron affinity. You will notice that in our normal trend, you see fluorine, you see chlorine, you see bromine, and finally, you will see iodine. These are all of your halogens. The halogens are actually the most electron affinity group in the entire periodic table because they are one electron short. That one electron can give them noble gas stability, and that is why they release so much energy upon the creation of the anion. So let's try this example to finish up this lecture. Why are the electron affinities for the alkaline earth metals either negative or very small positive values? So let's look at this periodic table and let's think of our beryllium. When it comes to our beryllium, we end up having our valence shell being the 2s orbital set. So now the electron affinity is going to talk about adding an electron. Well, I can't add an electron in the 2s subshell anymore, so now where I have to go is to the 2p's. Well, when it comes to the 2p orbital, putting this one electron all by itself is electronically unstable. So if you start to think about populating orbitals that weren't originally filled, this is what is going to give you poor electron affinities. In this video, we have seen a couple of very important trends that discuss electronic properties. The first being ionization energy that's creating a positively charged species by removing an electron. Our electron affinity is how does our atom react when we give it an electron? Is it happy and does it give off energy? Or is it going to try and fight us and we are going to have to try and donate some energy for it to take the electron? This now finishes up chapter 4, and now you've seen the importance of all the periodic trends that we have and that we will continue to build off of. Have a great day.